When you compare the reactivity of benzene and aryl halide, in case of aryl halide, halogen is bonded to benzene ring, and due to presence of lone pair of electron, it donates electron density into benzene ring through plus M effect. And at the same time, being electronegative, it withdraws electron density from the benzene ring through minus I effect. So overall, it weakly deactivates benzene ring, but still it gives electrophilic substitution like benzene. But how does halogen influence the addition of electrophile to benzene? When a substituted benzene undergo electrophilic substitution reaction, where does the new substituent get attached itself? It is decided by the substituent already attached to the benzene ring. For example, when aryl halide undergo electrophilic substitution, where does electrophile get attached to? It is decided by the halogen that is already bonded to benzene ring. Let's see how halogen guide the coming electrophile. Halogen donate electron density into benzene ring through plus M effect. Halogen has lone pair of electron, so it will donate lone pair of electron to benzene ring. As a result of it, double bond is formed between carbon and halogen, and positive charge is developed over halogen. Now this carbon becomes pentavalent. To maintain its tetravalency, this double bond shifts to the next carbon. As a result of it, negative charge is developed over this carbon. Now this negative charge transferred between these two carbon. As a result of it, double bond is formed between these two carbon. Now this carbon becomes pentavalent. To maintain its tetravalency, it transferred this double bond to the next carbon. And as a result of it, negative charge is developed over this carbon. Now again, this negative charge is transferred between these two carbon, and as a result of it, double bond is formed between these two carbon. Now again, this carbon becomes pentavalent. To maintain its tetravalency, this double bond is shifted to another carbon, and as a result of it, negative charge is developed over this carbon. When you closely observe these resonating structure, you will find out negative charge is developed over ortho and para position with respect to halogen. That means electron density on ortho and para position increases due to presence of halogen. Therefore, further substitution occur at ortho and para positions. That's why halogens are called as ortho-para directing groups. So when aryl halide undergo electrophilic substitution, electrophile get attached to either ortho and para position. When electrophile get attached to ortho position with respect to halogen, you will get ortho isomer. And when it will get attached to para position with respect to halogen, you will get para isomer. Out of these two isomers, para isomer is the major product because there is less steric crowding, while there is more steric crowding in ortho isomer. Now let's try to understand the role of halogen when electrophile get attached to ortho position. When aryl halide react with electrophile, electrophile get attached to ortho position, and as a result of it, positive charge is developed over the carbon that is bonded to halogen. Halogen has lone pair of electron, so it can donate electron density to benzene ring through plus M effect. When it donates lone pair to the benzene ring, double bond is formed between carbon and halogen, and positive charge developed over halogen. So that's how formed carbocation is stabilized by the resonance effect of halogen. But due to addition of electrophile, aromatic character of benzene is lost. To regain its aromatic character, it loses hydrogen in the form of H+ ion. Hydrogen will donate a bonding pair of electron to benzene ring, and the double bond between carbon and halogen move to halogen. And as a result of it, aromatic character of benzene is restored and electrophile get attached to ortho position with respect to halogen. Now let's see the role of halogen when electrophile get attached to para position. So this is the aryl halide. When electrophile react to aryl halide, electrophile get attached to para position, and as a result of it, positive charge will develop at the meta position with respect to halogen. As we discussed earlier, halogen has a lone pair of electron, so it will donate electron density through plus M effect. When it donates lone pair to the benzene ring, double bond is formed between carbon and halogen, and positive charge developed over halogen. And when this double bond moves to another carbon, negative charge will develop at this position. Now this negative charge shifts between these two carbons. So as a result of it, double bond is formed between these two carbons. This formed carbocation is stabilized by resonance effect of halogen. But the aromatic character of benzene is lost due to the addition of electrophile. To regain its aromatic character, again it loses hydrogen in the form of H+ ion. Hydrogen will donate bonding pair of electron to benzene ring. As a result of it, double bond is formed here. And when this double bond moves between these two carbon, new double bond will form here. And then double bond between carbon and halogen moves to halogen. Now aromatic character of benzene is also restored in the molecule and positive charge is also neutralized. So that's how halogen help the electrophile to get attached to para position. Now come to the reactions of aryl halide. First of all, we are going to discuss halogenation. Halogenation means the addition of halogen. Here I have taken the example of aryl chloride. When it reacts with Br2 in presence of FeBr3. Here FeBr3 is the Lewis acid. It is used to produce electrophile. So let's see how electrophile is generated by the reaction of Br2 and FeBr3. Fe abstract Br negative ion from the Br2. As a result of it, FeBr4 negative ion is formed and Br positive ion is formed, which act as an electrophile. As we discussed earlier, halogens are ortho-para-direct. So when electrophile Br positive get attached to aryl halide, either it get attached to ortho position and form ortho-bromo-chlorobenzene, or it can attach to para position and result in the formation of para-bromo-chlorobenzene. Out of these two isomers, para isomer is the major product because of less steric crowding in para isomer. Now come to the Friedel-Crafts alkylation reaction. For the alkylation reaction, alkyl halide is taken in presence of anhydrous AlCl3. Here AlCl3 is the Lewis acid that help to produce electrophile. So let's see how electrophile is generated by the reaction of alkyl halide and AlCl3. AlCl3 accept chloride ion from the alkyl halide and as a result of it AlCl4 negative ion is formed and CH3 positive carbocation is formed, which served as an electrophile. When electrophile get attached to aryl chloride, either it get attached to ortho position and result in the formation of 1-chloro-2-methylbenzene, or the other name is orthochlorotoluene. And when it get attached to para position, it results in the formation of 1-chloro-4-methylbenzene, or para-chlorotoluene is the other name of this product. Out of these two isomers, para isomer is the major product because there is less steric crowding. Now come to the Friedel-Crafts acylation reaction. For the acylation, you have to take acyl chloride in presence of anhydrous AlCl3. Now let's see how electrophile is generated by the reaction of acyl chloride and AlCl3. AlCl3 accept chloride ion from acyl chloride and as a result of it AlCl4 negative ion is formed and acylinium ion is formed, which served as an electrophile. It either get attached to ortho position and result in the formation of 2-chloroacetophenone, or it get attached to para position and as a result of it 4-chloroacetophenone is formed. Out of these two isomers, para isomer is the major product due to less steric crowding. Now come to nitration. First of all, we are going to discuss the generation of electrophile. Nitrating agent is HNO3 in presence of H2SO4. So I can write HNO3 as HONO2 and H2SO4 can be written as HSO4H. When you compare acidic strength of HNO3 and H2SO4, H2SO4 is a stronger acid. So it will donate H+ ion and nitric acid act as a base. So it will accept H+ ion. After accepting H+ ion, it will form H2O positive NO2 ion and SO4H negative ion is formed. When it loses water molecule, it results in the formation of NO2 positive ion, which served as an electrophile. We just have seen HNO3 in presence of H2SO4 generated NO2 positive ion as an electrophile. When this electrophile get attached to ortho position, it forms 2-chloro-nitrobenzene, and when it get attached to para position, it results in the formation of 4-chloro-nitrobenzene. Out of these two isomers, para isomer is the major product due to less steric crowding. Now come to the sulfonation. First of all, we are going to see how electrophile is generated in case of sulfonation. For sulfonation, two molecules of sulfuric acid are used as a sulfonating reagent. One of the molecule acts as a base while another acts as an acid. So the molecule that acts as an acid donate H plus ion, and the molecule that served as a base accept H plus ion. And as a result of it, this cation is formed. By the loss of water, it results in the formation of SO3H positive ion, which acts as an electrophile. When aryl chloride reacts with the concentrated sulfuric acid on heating, it produces sulfonium ion as an electrophile. Either it gets attached to ortho position and result in the formation of 2-chloro-benzene sulfonic acid, and when it gets attached to para position, it results in the formation of 4-chloro-benzene sulfonic acid. And out of these two isomers, para isomer is the major product due to less steric crowding.